Okay. Hi, everybody. My name's Greg Dobler from CFA. And thanks to Brice and Olivier for having me here. It's been really great. So today I'm going to talk about something that is maybe obvious, maybe not, depending on how much you've thought about it. And that's multiply imaged supernovae. And sort of the challenges that go along with measuring these things and interpreting them, some of the science that you can do, and stuff like that. Okay, so I'll start off by saying the time is almost now. As we all know, the next generation surveys are coming, and they have lots of great features. Like, for example, their most prominent one is time domain information, which is sort of essential when looking for lensed supernovae. They also have the usual advances like increased sensitivity, enhanced spatial resolution, and larger solid angle. So just a quick run through. There's pan-stars, which is happening right now, 30,000 square degrees, down to about 22 and a half. 7 to 10 day cadence, but that depends because it's rotating through filters also, so that's not 7 to 10 days per filter. And about an arc second or so seeing, a little bit less. Like revisiting the same point in the sky. And then 0.26 or so arc seconds per pixel. And then a little bit later there's going to be LSST, 20,000 square degrees, much deeper, much faster cadence, and I think I think 2 filters per night. I think Phil and I were finding that yesterday. Also about an arc second or so seeing, and well-sampled PSF. And then much in the future, and so these numbers should probably take with a grain of salt, I think. I think they're always evolving. But then there's SNAP, which goes much, much deeper, but over a smaller area. Okay, so this is a plot courtesy of Macedonia Guri. For LSST, basically the total number of lens supernovae you would expect, where you can observe the third brightest image above 24.5 in I band. And so the numbers that you expect are about 10 to the minus 3 or so per square degree per year. And so, you know, LSST has 20,000 square degrees, going to be observing for about 10 years. So, you know, you get about 10 to 20 per year times 10 years, about 200. So there's going to be a fair number of these things. I will get back to why the third brightest is important a little bit later. But yeah. That's like a single shot. So that's, I think LSST goes down to like I have 24-ish in like 30 or 60 seconds or 60 seconds or something like that. One of those two. And well, to jump ahead for 1 second to answer Gary's question, the third brightest is because you need a way to find these things in the first place. And so if you see a supernova go off, then you see another one go off, and then maybe you know it's lensed, and then you're sort of thinking about your third one. Unless you have a double, in which case you're thinking about your second one. But that's coming up later. Okay, so some scientific payoffs. What can we learn with multiply imaged supernovae? So first of all, you can break the profile. If you have multiply imaged 1As, then you can break the profile time-related degeneracy by getting the absolute magnification and get H0 very nicely, as Oguri and Kalani showed for galaxy scales, and Adam Bolton and Scott Burrows for sort of cluster scales. So this is just a plot from Oguri and Kalani's paper. So this is sort of the arrow ellipse on in the radial profile slope H plane from using the flux ratios alone, and then using absolute magnifications, so you get much tighter constraints. And then if you have either 1s or 2s, you can measure time delays, but of course there's this profile degeneracy issue. Then there's this cool new idea by Chuck Keaton and Lexi, who is going to talk about this later today, so definitely stick around for that, where substructure in the lens galaxies perturbs your time delay on the scale of like days or so, like a day or so, which may be measurable with LSST. And then well, it depends how well you can interpolate between the images to line them up. But that's another issue that we'll get back. going to definitely come back to in a few minutes. So if you have time delays measured, you can do also great stuff like constrained lens models. Well, it provides an additional constraint on your lens models. And you can follow up after the event. So the nice thing about lens supernovae is they fade away, and then you can go back and observe more deeply and see the lens galaxy behind it. And then maybe you can do some supernova physics if you're lucky, and I will get back to that later. Okay, so what can go wrong when you're looking for multiply image supernovae? So there's three basic things, I think, that can go wrong. There's resolution problems, depth problems, and especially time sampling problems. First of all, resolution. You will probably need about an arc second or less seeing, so that's not going to be so much of a problem for upcoming surveys because that is about the upper limit on what the seeing should really be. Famous last words, but that's about what it should be. So the resolution is important when you're actually modeling a lens system. If you're not going to do follow-up, there was a recent paper by Phil and I think Tommaso was on it and others about sort of ways to do the lens modeling without going back and getting ultra high resolution imaging. There's depth issues. So this is the issue of do you get a light curve versus do you just see a blip for a day or something like that. If you want to really do some nice time delay measurements and stuff, you really want light curves, so you can get these things to higher accuracy. Magnification helps, right? Because these things are being magnified by factors of a few or so, and the problem is well, problem or benefit depending on how you see it. More is more, and less is obviously less. So then time sampling is the one that's a little bit trickier to wrap your head around. So there's the time delay measurement, first of all, which Chris was just saying. It's not so obvious how exactly to line these things up in the first place, even without any other complicating factors, which I'll get back to. Plus there's this issue of filters, which are switching every time. So your single filter cadence in LSST, we were looking at yesterday, something like 9 days. And for pan stars, for example, it's much, much worse than that. And the duration of the survey comes into it. So it's okay for galaxy scale lenses where your time delays are like weeks to months to maybe a year. But for cluster scale lenses where your time delays are getting up to like a few years, then if you're observing for 10 years, then this is a real bias. And so that's the time delay selection bias. Okay, so that was very pessimistic. What can go wrong? So now I will talk about what can go right. So here are just a few ideas of how to actually pick out multiply image supernovae from some survey that's ongoing. So one idea is to look for supernovae that have different redshifts from what you think is their host galaxies. So this is in sort of increasing order of difficulty to do, I think. So this is going to require photos used for both things, so we're not going to have spectra with these surveys. And so, but the problem here is that in order to get a photometric redshift for a supernova, you really need to have information about the width of the light curve. And in most cases, it will be impossible, especially if your cadence is only a few days. Probably a little bit easier, and this is related to the one that in Masamune's plot, was if you observe the first two images, then you can go back and look for third and fourth images. So, but this requires a quad. But it is a way of identifying them. And lastly, probably the easiest one to do is look in a place where you already know or suspect that there is a lens, so that you have a higher probability that something is being multiply imaged. So, for example, there's clusters, which I'm not going to talk much more about. But then there's also galaxy lenses, the sample of which is increasing quite dramatically with time, as we heard earlier today. So here's the hope. Here's the hope for what you can do. So observe every few days and get good time sampling. Then sort out the info between the different filters and the resolution effects. Let the amplitude float, because these things are, the different images are magnified to different degrees, and then try to line up or interpolate the light curves to get a good measurement of delta t. And then after that, you do fun stuff like the follow-up and measure redshifts of source and lens and model the lens and drive it zero, et cetera, et cetera. So these two are from Lowry, Kirby, and Phil, and Masamune, and the LSST team. So this is fake data, fake LSST data of a movie of a supernova going off in an Einstein cross configuration. You see 1, 2, and then 3 and 4 kind of book their way in here. And so this is sort of, and this is sampling you would expect from LSST. And so you can see what you're kind of working with here. You're going to have to interpolate between these different light curves to try to measure time delays, which is a non-trivial task. So let me focus on that for a second. Let's assume you have infinite time sampling, in fact. Turns out that there is an additional complication, which I'm going to talk about for a few minutes right now. Okay, so here's an example. This is a SLACS lens, as I'm sure probably many of you have seen. So the idea is a supernova goes off in some place, and then it goes off in a counter image, and then another counter image, and another one, or something like that. But this has the lens galaxy subtracted. So this is the residual after subtracting the lens galaxy. The actual system looks something like this, right? So there's lots of stuff, namely stars, in front of that lens galaxy. And so the question is, what do those stars do to your light curves of your lens supernovae? So let's first estimate the fraction of the surface mass density in stars. Okay, let's take a isothermal profile for the total mass density and a de Vaucouleurs profile for the starlight density with some free-floating amplitude coefficient. Let's find the worst possible case. So let's normalize the de Vaucouleurs profile so that at some point that all of the mass is dominated by baryons. Okay, and so here's what you get as a function of the Einstein radius of the total mass density over the effective radius of the de Vaucouleurs profile. And so Leon, Koopmans, and the SLACS team found that for the SLACS lenses, mean Rn over Rf is about 0.52. So if you normalize your density profiles to 1, then at 0.52, the fraction of surface density in stars is about 0.57. So let's keep that number in mind. So now what about the source size of the supernovae? You know, if the supernova is very, the photosphere is very large in the source plane, then the stars won't matter so much. But you can work it out, and for the mean source and lens redshifts of the SLACS sample anyway, the Einstein radius of a stellar mass object is 13.13 light days, and the velocity of the photosphere of a supernova is between 10 and 15,000 or so kilometers per second from emission lines. And so the expansion rate in units of the mean Einstein radius is about 4 × 10⁻³ So over the course of the supernova's life, it will expand out to be about comparable to or a little bit less than the stellar Einstein radius. So fraction of surface density in stars 0.57 and 0.4 × 10⁻³ Einstein radii per day implies that microlensing will be likely in lens supernovae. So let's actually quantify that. So here are some caustic networks where these are positions in the source plane where the brightness corresponds to the magnification, and they're 2.5 Einstein radii on the side. And so over the course of its life, a supernova will go from being a dot to being about a third of the size of one of these. All right? And so the caustic network itself, as you can see, varies quite a bit, even for fixed stellar population parameters. So here are the realizations that we ran. So we have a stellar population saltpeter mass function, mean mass, solar mass, and we vary the mass ratio of the stars. And for a supernova, we assume a uniform brightness disk, the so-called expanding photosphere method. Velocity of 15,000 kilometers per second, and we run the simulations out for 250 days. So this is this is the images that will not be resolved. This is micro arcsecond scales here. So first you see a few dots, and then some more images pop into existence, and then as it gets bigger and bigger, some of the images merge, and out at 200 days, this is sort of what your image configuration is like. So now the light curves, the effect on the light curves, so these are now difference light curves. So these are defined as the change in magnitude compared to the magnitude you would expect from amplification by a smooth model. And so it has lots and lots of features as the photosphere is crossing the caustics. So some of these are offsets on the order of 1/2 to a magnitude. And then short time scale variations like these bumps here or here between 1/10 and 2/10 of a magnitude or so. And then longer time scale variations on the order of a few tenths magnitudes. Okay, so say you're putting those on top of a supernova light curve. So this is CSP, supernova 2004 EJ. So I don't know if you can see the difference between the dotted and the solid, but the solid is the unmicrolensed case, and the dotted is the microlensed case. So what you get is you get overall offsets, you get additional little features, you get small perturbations, you get changes to the decay rate. So lots of different things can happen to your supernova light curve. Okay, and so now here's varying the mass ratio in your mass function for your stars, and also your stellar mass fraction. And basically, you see those same features that we were seeing before for all values of F star and Q. So that is, all light curves show fluctuations. And to quantify that, if we look for the maximum perturbation to the light curve, that is the ratio of the minimum perturbation to the maximum perturbation, so delta max as we defined it here. It's a probability distribution function and cumulative distribution function. The bottom line is that for 75% or so of the light curves, you expect half a magnitude fluctuations or more, and about 25% you expect about a magnitude fluctuation or more. So these are definitely observable. And so going back to what the hope was, the hope is that we could line these things up and interpolate them. Turns out that the reality is that that's going to be very difficult, even if you sampled every 5 seconds. So we oversampled the light curves, added the microlensing, and tried to line them up. And it turns out that the widths of the widths of the histograms you get when you try to infer the time delay, which is originally 16.5 days, are on the order of a day and a half to more. Okay? So these fluctuations due to the microlensing lead to order more than a couple days uncertainty in the time delay. So let me briefly say as an aside, or rather I'm almost finished, so it's kind of a conclusion, that for pan-stars especially, things like catalogs of candidates will be important for this. So there's photometric searches for galaxy-galaxy lenses. Lots of people have done HST stuff. There's also the counter-French Wide telescope stuff. And then we heard this morning great stuff, which actually I was not aware of, by Mike Ladders and Howard Yee, about how many galaxy-galaxy lenses there are in the RCS2 data. Then there are spectroscopic searches going on. Of course, SLACS is probably the most well-known. But then BOSS is going to come online soon. If you haven't heard of BOSS, it's the Baryon Oscillation Spectroscopic Survey. That's being headed by Dave Schlegel, I think. That's sort of a after Sloan 2 project. And it's going to measure 1 million LRG spectra at slightly higher redshifts. And one of the issues, though, is that it's going to have a smaller fiber diameter. So I'll say more about that in a slide or so. But the point here is that we need that generating a catalog of systems for potential follow-up would be nice. So basically knowing where to look. And so you see a supernova go off in a system you know is a galaxy-galaxy lens, giving you a higher probability that it's actually will actually be a multiply image system, and then you can go tell whatever telescope you want to go look at the system and wait for the counter images X number of days from now, because you have an idea of what the time delay should be. So about the spectroscopic searches, and BOSS in particular, well, let me first talk about SLACS. So here's the idea. You're here with a spectrograph and you're looking at a galaxy. So what's the probability that there is some galaxy in the Einstein cone? There's a background galaxy in the Einstein cone of this foreground LRG. That's just the integral of the number density over the volume in the Einstein cone. And so that's an integral over redshift, distance behind the galaxy, and then an integral over the source plane, which is where the magnification comes in. And the fiber, actually, so what the fiber is doing is cutting off this Einstein cone in certain spots. And so, for example, if you have a system that has the images inside the fiber, you're getting all the flux. If you have a system where one of the images falls outside the fiber, you might lose a lot of flux. But then, of course, there's seeing, which throws some flux out of the fiber and some flux back into the fiber. So there are lots of things that come into this. And so the fiber size introduces complicated selection effects. For example, as you might think that as you increase the mass of an LRG, so basically increase its velocity dispersion, you'd be more likely that LRG would be a lens. That probability does not increase monotonically with velocity dispersion because of these fiber size effects. And the luminosity function is also very important. So for the luminosity function of the source, right? Because you're looking for rogue lines in otherwise well-behaved LRG spectra. So the luminosity, these are probabilities of finding an O2 line in a given LRG for different values of a sort of an evolution parameter of the luminosity function. And this is the probability that LRG is a lens. And so BOSS has a different fiber size, and it's at different redshifts. But basically, with 1 million LRGs, you'd expect out about 1,000 LRGs with rogue O2 and O3 H beta lines, et cetera. And so that gives you sort of a potential target list. Right? So without actually going back and following up 1,000 systems with HST, because that's impossible, these are sort of higher probability than average that a supernova that goes off near one of those LRGs is going to be multiply imaged. Okay? So my very last slide will be intense speculation. But what about a lensed GRB? So I'm not talking here about optical counterparts or afterglows or something like that. I mean the gamma rays themselves, right? So GLAST is going to observe about 100 or so GRBs per year, give or take. It's going to be observing for a few years. So the probability is not 1 in 1,000 that they'll see one, but it's not very high. Could be. But these things last for like 1,000 seconds or something like that, right? So you get great time delays. You barely have to worry about matching up your gamma ray images. And even if you did, they have very sharp, nice features that are going to be resolved by GLAST that will be amenable to lining things up and that can't be reproduced with microlensing. So in case you missed it, yesterday, this is GLAST launching into space at 12:05 p.m. Eastern Standard Time. And that's all I'll say.
Oh, wait. I'll do somebody else first. Mike.
Yeah.
So the calculation, if I remember it, is that if you wanted to see a multiple image supernova in an arc behind a cluster,
yeah.
so a cluster scale is, you sort of have to look at 100 of those systems for a year, and you might see one.
That's right, because the supernova rate's like 1 per 100 years.
And now, this microlensing issue on time delays and the sort of decreasing variability in the light curve as the supernova itself expands.
Yeah.
I remember talking to Chuck about this years ago now. Could you, in cluster scale lenses, use that as a way of probing small scale substructure in dark?
In fact, I'm working on that as we speak. So if you have a cluster, not as we speak. Yes, right now. Hold on, I have to stop my coach here. Yeah, so if you have a cluster, so this is one of the things that maybe we can do with pan-stars with some of the staring fields, where we come back to them every single night. If you have a cluster and you have background light going through the cluster, actually, and you have supernovae from weakly lensed things even, and they're going through a lot of mass density, the wiggles, so you can extract information about the small scale structure from those wiggles. I didn't talk about it, but there are some statistics that you can do. Then if a weakly lensed supernova has wiggles in it, then if you can sort out the intracluster light properties, then maybe you can probe machos on very small scales or something like that.
Aren't your microlensing fluctuations the easiest way to find a strongly lensed system? You know that it's a background supernova in that case. So
Yeah, sure. So you mean like a supernova, but you have to be...
Light curve, if you see a fluctuation relative to the template greater than 10, you say, this is almost certainly a background source. We'll follow it up as a second.
Yes, assuming that you trust your templates to the point where you can identify perturbations and say, okay, I think that's...
Like when you were throwing away all of the other things that don't look like a supernova template, that don't look like a supernova.
Right.
I bet you can do it if you think you want to.
I mean, it's hard enough with the supernova, the SDSS supernova, we even look at one supernova.
Oh yes, you have to see the sociology if that's the thing. Yeah.
Right, exactly.
You can certainly pick up the second one.
Phil?
With a few day time delay precision, if you don't attempt to model the microlens, how do you think you can do it if you do model?
The answer is I'm not sure. So what I can say is it's actually a lot better for things like plateau, 2P supernovae. The reason is because if your supernova has a sharp feature in it, if your light curve has a sharp feature in it, those things, especially sharp drops, you can't make those with microlensing. Okay, so microlensing can give you sharp increases as your supernova is expanding and hits a caustic. You can get a big jump, and in fact, in some of those different light curves you're looking at, you can see steps, kind of like sharp increases in the magnification. But you never get a sharp decrease in the magnification. Okay, so if you have a plateau and you can identify where the thing is falling down, then you can do very, very well.
But the plateau supernova is sort of special anyway because the source side isn't changing during the plateau.
It's not changing, or it's not changing very much.
It would feel like,
No, the source size is always changing. It's the conspiracy you have between the size and the opacity that sets the plateau.
Okay.
They're always expanding.
Size effects. Size effects.
So, but in terms of like modeling the microlensing and getting rid of the microlensing from a supernova light curve, I'm not entirely sure. I mean, because you can see some patterns in the difference light curves, and like I said, we did some statistics that I didn't show, basically related to derivatives of those things. And it could be that you could make some sort of templates for those for the microlensing.
I guess you need
But-
pretty okay.
Yeah, you need very high cadence to separate out those kinds of fluctuations from just regular supernova features.
And you need a lot of computer power.
And you
for
need
every
it,
single event.
as Chris knows well, you need an awful lot of computer power. Yeah.
So, early in your talk, your list of things are more and more difficult.
Yes.
And I believe you said the most difficult thing was to sort of pre-identify a set of places to look.
No, that was the easiest one.
The easiest.
The hardest one was getting photo Zs for the foreground galaxy and the supernova.
I mean, do you actually expect often to see a multiply image supernova where there isn't an obvious lensed background source to begin with? I mean, type 2s occur in starform regions that are high surface brightness, and type 1s occur in
So the optical depth,
galaxies to first order.
the optical depth to multiple imaging is like about 1,000, 1 in 1,000 to 1 in 100ish, somewhere around there, right?
The optical depth is all in the LRGs, right?
Right, that's right.
So, you're looking for supernova in LRGs.
Yeah, you're basically
Oh,
looking.
you have type 1s.
Right, but will you see a multiply image supernova often where there's no obvious multiply image background gaps?
No. Well,
Do you-
it can be hidden
Right.
underneath the LRG.
Yeah, yeah,
Depends on
right.
your surface brightness sensitivity for finding the host underneath the LRG.
Yeah.
For example, in the SLACS lenses, you don't see the blue arcs in the slow images. But in the CFHD legacy survey, and I guess in RCS2, you see a whole
Probably
load of
would.
LRGs that have blue smokers in.
Right.
You couldn't say for sure whether it was an actual strong lens or not, but they would be good things to monitor with something like this.
I mean, if you don't want to pay attention to the entire sky,
Well,
Two
it's
days.
also a question of whether you want to retrospectively identify them or flag them for better marking.
That's right. I think that's the point I was making with the third one. So looking at places where you know they already are. I mean, if you want to do stuff like catch the supernova in like the first hours or so, right, where the photosphere is very, very small. So if you are seeing fluctuations there, you're probing really small scale structure in the lens potential, right? If you want to do that, then you need to tell a telescope on the ground to look at it at a given specified time. And if you want to do that, you need to flag that supernova as being potentially important for follow-up.
But I mean, supernova people are good at telling what type of redshift a supernova is by just the photometry on the rise, because that's how they decide.
Right, but if your cadence is every 5 to 10 or more days in a given filter, right? Because you need sort of the width in different filters, right? And so if you don't have that, then you're only going to get 1 or maybe 2 points on the rise.
Yeah, 10 days is going to be a long time
Yeah.
for a low redshift supernova, but
Yeah.
4 days.
Remember, it's the rise that might screws up.
Exactly, and that's the thing.
Yeah, so you would prefer them to have a strategy where colors are all taken at the same time.
Yeah, but that's not going to happen with LSST or pan-stars.
Colors are also.
Well, yeah, well, does the size of
It's the
supernova
photosphere.
photosphere depend on its the way it comes off the wavelength?
How well can you, and what would you need as far as saying, one image seen already, 2 images seen already, to be able to make some reasonable prediction for when a third or fourth is going to show up? I mean, say in a cluster system where you have.
Oh, well, that depends on how good your lens model is, I
Right.
suppose. And then in cluster systems, I mean, the time delays are, first of all, in cluster system, the time delays are long enough
Right.
that the duration of the survey starts to become an issue in most
Well,
cases.
if you could predict, then you could go back later.
Exactly, yeah, you can definitely do that, but then,
We haven't tested this with SDSS 1004.
right.
So far, the track record of theorists and predicting the later measured time delays is not encouraging.
So this is for measuring the time delay of the quasar, yeah.
And does it get harder or easier going to clusters, going to larger systems?
It would be easier in galaxies than clusters.
Right, because small changes to potential gives you correspondingly bigger changes in your time delay.
There's
Exactly.
Plenty of time to plan the
Lots of time
Right,
to
but
model.
what Lloyd was saying was you see a couple images and then your survey ends, but to go point GMT or something at this place. Right.
I think the art one thing focus is really kind of morphology within the same art, a few merging images.
Yeah.
The time delays are not so.
Yeah, then the time delays are not like, they're not years and years and years.
None of the models have the time to make the merging pair in 1004.
No, I agree. Catching things on the road, but just
But of course, in clusters, okay. So say you're ignoring the small scale structure of dark matter, if there is small scale structure of dark matter, like very small scale, compact structure of dark matter, then the microlensing issues kind of go away, because then all you have are just intracluster light stars. So.
Which are a very small fraction.
Which are a very, very small fraction. So if you see, as I was saying, if you see fluctuations in your weakly lensed light curves, then that's something.
But this microlensing, if you have these huge time delays, then the microlensing effects don't mess you up as far as a fractional measurement.
That's right.
All right, let's thank you again. Thank you much.
All right, so we'll